Take a look at the at work and energy and how work causes a change in the kinetic energy of an object. Here's a situation where we have work being done by force of gravity to increase this roller coaster's velocity at the bottom of the hill. Work done by constant force is what we're going to look at first. If a person pushes on a car with a certain force for a distance, in this case they're using the variable s, that's common in physics to use that s. Work is accomplished with this force acting over a distance s. The equation for work is that force times cosine theta times the distance. It's force times distance. And the force has to be in the same direction as the distance. That's what the cosine theta is about there. Theta is the angle between the force vector and the displacement vector. And you'll see this displacement vector is horizontal, the force vector is horizontal, so the angle between them is 0 degrees. Cosine of 0 is 1, so really it does not change the force value at all. It's just force times the distance. On an example here, when the force and the distance are in different directions, we're going to find the work done by a 45 newton force and pulling the suitcase at an angle of 50 degrees, and that 50 degrees is to the horizontal, for a distance of 75 meters. The equation is work equals F cosine theta times the displacement. So that's 45 newtons times the cosine of the angle 50 degrees times the 75 meters gives you 2,170. And the units here, instead of being newtons times meters, which is a newton meter, they give the units called joules. That capital J is joules, J-O-U-L-E, joules. It's named after a physicist. The next example I want to talk about here is the weightlifter in figure 6.3a is bench pressing a barbell whose weight is 710 newtons. In part B of the figure, he raises the barbell a distance of 0.65 meters. And in part C, he lowers it the same distance. The weight is raised and lowered at a constant velocity. Determine the work done on the barbell by the weight lifter during the lifting phase and the lowering phase. Now if you look at picture B here, you'll see the force vector is straight up, the displacement vector is straight up, so the angle between them is 0. And so we have here work equals F cosine theta S, so we have 710 newtons times the cosine of 0 degrees times 0.65 meters equals 460 joules. The next one you'll notice the force vector and the displacement vector. This is when the barbell is coming back down. The displacement from where you start to where you end is in that direction, so we use 180 degrees, not 0 degrees. The cosine of 180 degrees is negative 1. And you'll see here that the work then would be negative 460 joules. So if you were to add up both of these together, you would get an answer of 0. And that hopefully makes sense because the barbell started right here at its chest, and it ends right here at its chest. So there's really no net work done. All of the where you started is back where you ended. Or you ended back where you started, so the total amount of work accomplished is 0. Here's another problem that we use friction with. We show a 120 kilogram crate on the flatbed of a truck that is moving with an acceleration of 1.5 meters per second squared along the positive x-axis. The crate does not slip with respect to the truck, as the truck undergoes a displacement whose magnitude is 65 meters. What is the total work done on the crate by all the forces acting on it? Well, the easiest ones to look at first are the normal force and the weight. The displacement of this object is only in the x direction. So the work being done by the normal force, which is in the y direction, has to be 0. This crate does not move in the y direction at all. So the normal force done, or the work done by the normal force is 0, which also means the work done by the weight is 0. So the only work being done is by this static frictional force, which is causing this box to move forward. If there was no friction between the bed and the box, this box would slip off the car. So that's the force of friction is what's causing this thing to move forward. So we're going to go ahead and solve this by using work equals force times distance. find that force, though, we have to do mass times acceleration. Force of that friction is mass times acceleration. It does it. We're not using a mu. We're just treating this just as a regular force. 120 kilograms times 1.5 meters per second squared is 180 newtons. And now we can use our work equation. 180 newtons times the cosine of 0 times 65 meters. So we end up with work being 1.2 times 10 to the 4th joules. Now we're going to look at something called the work energy theorem and kinetic energy. We have to know the definition of kinetic energy first, or it's actually the equation is 1/2 mass times velocity squared. So a mass that has motion will have kinetic energy. It's 1/2 the mass times the velocity squared. The work energy theorem says, so we have this initial value, kinetic energy initial, which changes to a final value, kinetic energy final. So its velocity is changing. It's going from one kinetic energy to another. The difference between the two values being equal to the work. So what this theorem says is that work, the net work, the total work done by all the forces together acting on an object will cause the kinetic energy of an object to change. And that's what this here says. Work is equal to the change in kinetic energy, which equals 1/2 mv squared minus 1/2 mv squared. So here, for example, there's a thrust force here by the engines of this jet, and we have initial velocity, and we have a final velocity, and then if you find out what the two kinetic energies are, or the difference between the two, that will give you the work done by the engines. So we're going to try a couple problems here. This particular problem is dedicated to Kristen for her driving abilities. And we're going to go ahead and figure out how fast this car was going using this kinetic energy theorem. Let's write down our givens and go from there. And we're going to approach this problem using the kinetic energy theorem. You can do this problem with just F equals ma and kinematics. But actually, the two are one and the same thing anyway. So we're just going to approach this problem using work equals a change in kinetic energy, just to see how to do it a slightly different way. And we have our force times our displacement. We can call that delta x. They call it s beforehand. You can call it d. There's various ways of solving for it. And we'll have 1/2 mv squared minus 1/2 mv squared, and this is final minus initial, so we have our initial there. Let's go ahead and for our force, we know our force is the force of friction, which actually is mu times normal force, which we know equals mu times, and this, if you look at this picture, it's mu times mg. So we're going to go ahead and plug that into our force up here of our force of friction. So we have mu mg for our force of friction times delta x equals 1/2 mv squared minus 1/2 mvo squared. And now we're going to go ahead and cancel out our masses. And we can now plug in values and come up with our answer. We have mu is 0.5, gravity is 10 meters per second squared, our displacement is 65 meters, 1/2, our final velocity is 0, and our initial velocity is what I want to solve for. Okay, and this force of friction, actually, I should have this equation up on top should be a little bit different. It should be force times cosine theta times our delta x. And when we have our cosine theta, we plug this in here, we'll have 180 degrees, and that's what's going to make this negative, because our force and our displacement are in opposite directions. So we would have down here, we would have mu mg cosine theta delta x. And if I had my cosine, my m would cancel along with those other m's. But I would have a cosine theta right in here. That would make it negative. Or I could just realize, what I'm going to end up doing is I'm going to end up realizing that force, whenever force and displacement are in opposite directions, it's just going to be negative work. So anyway, you have 0.5 times 10 meters per second squared times the cosine of 180 times 65 meters. And that cosine 180 is, if you know that they're in the opposite directions, you can just make that a negative and not have to write cosine 180. But anyway, if you go ahead and solve all that, you end up with initial velocity of 18 meters per second. Okay, let's take a look at the next problem. What we have here is a 58 kilogram skier is coasting down a 25-degree slope. The kinetic frictional force is 70 newtons, and it opposes her motion. And near the top of the slope, the skier's speed is 3.6 meters per second. Ignoring air resistance, determine the final speed at a point that is displaced 57 meters downhill. And so we have our free body diagram of the skier right here, showing us all the different forces that are acting. The normal force and mg cosine 25 actually do no work because this person, the xy axis is this way, and this person is not moving up or down in the y-axis. So this person is not moving up and down, so no work is being done by either of those forces. The work being done is by the force, kinetic frictional force, and the mg sine 25 force. So let's go ahead and take a look at our equation. Work equals the change in kinetic energy. And work is being done by two forces. So we have the work being done by the kinetic force and the work being done by mg sine 25. So let's go ahead and write that out here. We have the kinetic force times cosine theta times the distance. Call that S for this problem. And we have the work being done by the next force, which is mg sine 25. Times cosine theta. And I'm going to write this down here to give me more room. So we have our mg sine 25, and I put cosine of phi because it's it may be it's going to be a different angle that we work with here, and times the displacement equals the change in kinetic energy, which is 1/2 m v final squared minus 1/2 m v initial squared. And now all we really have to do is just plug in our values. Now the kinetic friction force we know is 70. So let's go ahead and plug in our values. We have 70 newtons for our kinetic friction force. Our cosine is 180 degrees because the direction we're going in is downhill, but the force of friction is uphill, so that's 180 degrees. Cosine 180. The displacement is 57 meters. mg times the sine of 25. Well, it's 58 kilograms is the mass. So that's right there. Gravity is 10 meters per second squared. So that's 580 newtons times the sine of 25, which gives us a value of 245 newtons. Not 248, 245 newtons. Times the cosine, in this case, of 0 degrees, which is 1, times our displacement S, which is 57 meters, equals 1/2. The mass is 58 kilograms. The final velocity is what I want to solve for. 58 kilograms And the initial velocity we know is 3.6 meters per second. And that's squared. So we go ahead and do the math there, and we come up with a final answer equaling 19 meters per second.